Welcome everyone to my new lecture where we are going to learn about the capacitor. Capacitor is a device that is made out of two conducting plates that don't touch each other. Between those two plates is an insulator. Capacitor can store electrical energy, and that capability to store electrical energy is called capacitance. And this is the formula for capacitance. That's equal to the charge on these two metal plates divided by the voltage between those metal plates. So let me show you. Here we have a battery, U minus, and now we have these two metal plates, and between these two metal plates that are conducting metal plates, okay, every metal is a conductor, we have an insulator, for example, air. So here you will have a plus charges, see, because you have here plus, 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 and here you will have minuses. So all these charges are gonna form on these two metal plates. And now we have a capacitor here. So for example, now we remove this battery here, okay, and let's say we're gonna put here a light bulb. Now these electrons, these minuses, are gonna go through this light bulb and go to this plus sign. So let me just plus sign. So this negative charge is going to go through here. So you have directed movement of electrons. Then you will have a current flowing, and this light bulb is going to turn on. But every plus and minus is going to cancel each other out. So you get an atom. So you don't have no more charges. And so this disappears, this disappears, this, and that becomes, again. So every minus and plus is going to cancel each other out, and now you won't have any charge here, and now the light bulb is going to turn down. So capacitors are the devices that are used to store electrical energy. Okay, so this is the formula, and it's measured in farads. 1 coulomb per volt is 1 farad, but it's usually measured in nanofarads, picofarads, microfarads, because 1 farad is a very high unit. Okay, so I'm not gonna. I guess you learned what capacitor is. And I'm not gonna remove all this, so because there are a few more formulas to write down, and maybe we'll do some examples. Okay, so for example, let me just take my book. See here. Okay, the insulator plays a very big part in a capacitor. So we have two metal plates. Okay, we have, I don't know, we have, I don't know, an insulator, that's it. Okay, so you have here plus and a minus, and that's that, okay, no. But if you put another insulator, for example, some kind of liquid, I don't know, then you will have a polarization. And you will have a stronger electric field, and you will have more capacitance. Now you will see the formula. You have a liquid, and the positive parts of this liquid is going to go right here. And the negative is going to go right here. They want to they attract each other, plus and minus attract each other. So now we have another formula for the capacitance of a capacitor, and it is next. C, capacitance is equal to the okay, so one more second. The insulator, we usually in electrical, the insulator between these metal plates that conduct electricity, not electricity, that conduct this electrical charge. The insulator between those metal plates is called a dielectric. So now we have here dielectric. Is equal to epsilon index R, epsilon 0 times the area of the metal plates. Both of these metal plates must be, both of this area of these metal plates must be the same, divided by the distance of these two electric metal plates. So the epsilon 0 is the dielectric constant of the vacuum, and that's a constant, and the value of this dielectric constant is 8 times 8.854 times 10 to the minus 12 farads per meter. Okay, this epsilon R is the relative dielectric constant, and its value is 1, 2, 3, 4, 5, and there's no unit that stays with this number. So, for example, the relative dielectric constant for air is 1. So when you have air that is a dielectric between those metal plates, you have 1 times epsilon 0, but that's, epsilon 0, because 1 multiplied by anything is that number. Okay, this A is the area of the metal plate. And it's measured in meters squared. So this relative dielectric constant, it's always given in the example. See, you can find a table of all kinds of dielectrics. And D is the distance between those two plates. Okay, I want to find one example. Do. Well, actually, no. These are very easy examples. So I don't want to do it because it's really. Or maybe okay. We are gonna do one. We're gonna do one example. For a second, it says, what is the area of one side of a metal plate of a capacitor if the capacity of this capacitor is C equals to 0.02 times 10 to the minus 6 farads. We want to find the area. If there is a relative dielectric constant that is equal to 3.5, and the distance between the plates of a capacitor is 0.06 centimeters. So now we see, if you want to have a bigger capacitance, you want to make a shorter distance between those two plates. Okay, now you can see that A is equal to C times D divided by epsilon R epsilon 0. Epsilon 0 is always the same, and then you will get that this is equal to when you put all these values in here, you'll get that the area of this metal plate is 0.3872 meters squared. So that's the area that's the area of these metal plates. Okay, and one more thing to do. Where we connect, how we can connect capacitors in parallel. For example, here we have capacitor. And if you want, here we have three capacitors, they are connected parallel. If you want an equivalent capacitor, then that's just the sum of all these capacitors. For example, you now have three. But if you have capacitors in series, so the equivalent, sorry, I use my language, is equal to 1, like this. So this is how you measure in parallel the equivalent capacitance of these parallel capacitors, and this is in series. If you want more capacitance, then you connect capacitors parallel. If you want to lower down the voltage in these capacitors, then you connect in series. Thank you very much. See you in my next lecture.